Morning, this is the Chapter 3 review for electricity and power supplies from my A+ hardware certification class. This review is intended to be the last time we talk about this subject prior to the Chapter 3 test, and I'll go over all the things that we covered in Chapter 3. First thing we talked about in Chapter 3 was computer cases, and in particular form factors. It was our introduction to form factors in this class, and the fact that this is going to be a topic that we touch over again and again and again throughout the course, and understanding what a form factor is important throughout the course. So form factors describe the size, shape, and general makeup of a hardware component. It is what determines whether things are compatible, whether they fit physically, whether the plugs go together, and overall making sure we understand the form factor of our components is a very important part of the class, because if you go and buy memory that doesn't fit your motherboard, then you didn't understand the form factor of the motherboard. If you buy a case that won't hold your motherboard, then you didn't understand the form factor of the motherboard again, and the case related to it goes along with power supplies, and many of our components form factors apply to. Form factors have to make sure that the motherboard, the power supply, the case, and other items match. When we look at the form factor of a motherboard, we're going to learn in Chapter 4 that the motherboard form factor determines the kind of CPUs that can be plugged into it, the kind of memory that can be plugged into it. So we're going to see the idea of form factors coming back again and again throughout this class. Most of the time when we buy and build a new PC, that motherboard drives the decision for the other components. Could you go backwards? Of course you could. You could say, I want this CPU, therefore I get a motherboard that fits, and then it goes out from there again from the motherboard. Okay? But in all, the motherboard is what has to fit, the power supply has to fit the case, and then the CPU goes with the motherboard, the memory goes with the motherboard. Those things all have to match up. So the motherboard also determines what the system can do. We can always expand on that with some things. We talked about that in Chapter 1, what expansion cards and expansion slots do. But if you buy a motherboard that doesn't have any expansion slots, then you have no expansion capability. So the motherboard defines those things about our system, and the form factor that we choose goes along with that. So we talked about a couple of different form factors. I already mentioned this. It makes sure it fits the case, and make sure the power supply is the right connector for the motherboard, as well as the voltages required. And in this case, we're going to talk, or this chapter, we're going to talk about the wattage required for the entire system as well. Talked about how the holes have to be aligned with the case in order for it to even screw it in. We don't duct tape motherboards down to cases. We screw them with risers and spacers to make sure they're properly seated, properly grounded to our case. So we have to make sure those holes in the motherboard align with the holes in the case, and make sure that in the case of some, that the wires for the case match up with the wire connections on the motherboard, so that we can actually turn it on and have those things turn on and work. There are a number of different form factors out there, and these are just a few: ATX, Micro ATX, Flex ATX, BTX, LTX. There's lots. But I said before, the one we focus on in this class is ATX. It's the most prevalent, the most common, and the one that you probably have in your house. I'm not saying that everyone we have here at National Trail is one, because it isn't. We've got some specially sized ones, we've got some micros, we've got some LPXs. But those things define our size, our hole placement, our power. And in order for us to really concentrate and make sure we're staying with one form factor throughout the parts process of this course, we're going to predefine that ATX is what we're going to use for what we're doing in this class. ATX has been around for a long time. It came out in 1995. The core size was that, but there are lots of other sizes than 12 by 9.6 inches. It was designed in a way so that it avoids hardware interference. And this is the definition: the CPU and the memory slots avoid interference with the expansion slots. And we're going to see some pictures, but we know from our discussion that we've got our integrated components, our CPU, and our memory all in a row, so that these expansion slots don't get in the way with that part of the computer. It's to deconflict those things on our PC. Power supply and motherboards use a P1 connector that's either 20 or 24 pin, as well as a separate connector for the CPU. I don't know what just happened with my C there, but as well as one for the CPU in modern motherboards. And in the case of ATX form factors, the power supply blows air out of the case, and that's one of the things that we talked about in the class as well as far as cooling. Now, like I said, in ATX cases, there's a very specific alignment of things, those being the external connections, our CPU and our memory, with those expansion slots being out of the way of those things to deconflict them for us on our ATX configuration. We've got a specific power plug in an ATX. This is a 20 pin, but it could be 4 larger, it could be a 24 pin, and then the connector for the CPU power on the motherboard can either be 4 or 8, depending on what the motherboard requires and the kind of CPU that's on the motherboard. We talked about power and AC and DC power. The fact that AC is what we use on our wall outlets to transmit electricity. AC stands for alternating current, and it alternates at 60 hertz or 60 cycles per second. It is the most efficient way of transmitting electricity. And on our regular outlets, we get 110 volt AC power at our regular outlet. DC power, a direct current, only travels in one direction, and it's the best thing for electronic devices and for electronic circuit boards. So we have to turn that AC power into DC power, and we do that again through our power supply, which both rectifies it, which it turns it from AC to DC, and then it transforms it into different voltages that we need on our power supply. And those voltages we know are 3.3, 12, and 5 volt plugs. So our power supply is a transformer rectifier. It rectifies AC to DC and then transforms it to the voltages we need when we plug things in. We also talked about the different terms when it comes to electricity. We talked about volts, which is the potential difference in a circuit. And I gave you an analogy in class on that with the water pipe and the spigot and the bucket. And on my analogy, the voltage was the size of the hose that was plugged into our house. The diameter of the hose that was plugged into our house is the potential for water to come out. And then we talked about amperage, or electrical current. And I said that would kind of be how open we make that spigot on our house, the flow of water that comes through that hose, and the total amount of water or power, wattage, that comes out is that voltage times amperage equals wattage. And wattage is total power, calculated by multiplying volts and amps. And I gave you that analogy to try to help you understand the idea of potential versus total power. That voltage is the potential of electricity, amperage is the current of that electricity moving past that potential or through that potential, and wattage is the total that we get out of that. We did talk briefly about ohms or resistance, and I said we're not going to talk about a lot of that in this class because we're not talking about making circuit boards in this class. We're talking about repairing PCs, and although resistance comes into play in a variety of different places, it's not a huge item for us. We want to understand volts, amps, and wattage in this class in particular. We also talked about in this chapter the fact that electricity can damage our components, and that we have things that we can put in place to protect our electrical equipment from different kinds of electrical problems. Okay? And we talked specifically about 3 different kinds of electrical components or things that we can plug in. And the first one is a surge suppressor that looks like a power strip. We pass that around in class so you get a chance to see the difference between a power strip and a surge suppressor. It looks almost exactly the same. The difference is that a surge suppressor protects us from spikes. What is going on? I think I'm hitting my button while I'm doing that. It protects us from spikes. It has a clamping voltage on it. And I talked to you in class during the session that we talked about this, on the fact that I would always get one, that the higher voltage is great, but I would always get one with a warranty on it because they're not that more expensive. And that helps protect your equipment or replace your equipment if something happens. So surge protectors, surge suppressors only protect against spikes. They're only effective if you have them in a grounded outlet. If you have them in an ungrounded outlet, it's doing nothing other than being a really nice power strip for you. Power conditioners then protect against the next thing, and that's brownouts. And brownouts are, as we know, temporary reductions in voltages. They're the opposite of spikes. A spike's a temporary increase. A brownout is a temporary reduction. Not a complete loss, just a reduction, just to set the two apart. Okay, so power conditioners protect against brownouts. They also protect against spikes. This is kind of an increasing scale here. But when we talk about them, when we think about surge suppressors, they're made specifically for spikes. Power conditioners are made for brownouts and also help protect against spikes as well. The best thing that we can buy is an uninterruptible power source, or a UPS. They protect against blackouts or the total loss of power by having batteries inside them that provide a temporary source of electricity during a power outage. They only last so long. We did a walk around in the school. We saw the different UPSs in the closets and ones that are at specific desktops. UPSs are great. They only last about 3 years. The battery life on a UPS is about 3 years. After that, they start to degrade a lot. So you have to kind of keep track of how old your UPSs are. But they're the only thing that protect against blackouts. But again, they protect against those other things as well. UPS is made for blackouts, but obviously if it can handle zero power, it can handle a decrease in power or a brownout. And they also provide excellent protection against spikes as well. So uninterruptible power sources provide all 3 of those. They're made for blackouts. And a SmartUps, we talked about that in class, is one that connects to your computer and tells your computer to shut down. Mine's hooked up to mine, and when there's 2 minutes of electricity left, it automatically runs a shutdown. So it isn't like you just yank the power out of the back of the PC. So that's the difference when we look at a SmartUps. We talked about what to consider when we looked at UPSs, and I kind of got ahead of myself. So here we'll go back. Power suppressors, outlets, shut or absorb. They have a specific amount of electricity they can hold or clamp against. Power conditioners do spikes, but they also do brownouts or temporary decrease in power. And I just said this as well. Offers filtering AC. We get really nice ones. They're called sine wave filters, and they provide really good filtering of AC, meaning that they match the sine wave of the AC power and make sure it stays exactly the same during any kind of a power change. So they do a really nice job at that. So the SmartUps, I already said this, they monitor the load, they can figure out how long it takes or how long they'll be able to continually give power during a blackout. Some of them provide remote startup as well, that you can dial in and tell them to start the devices that are plugged into it as well. And then I didn't have a slide for the next thing. The things to consider with an UPS are that volt amp rating. The higher that rating, the more power it can provide and the more things it can keep running during a power outage. Our ones in our closet are a 2200 volt amp, and they are able to maintain our switches for over an hour along with our camera equipment, so that if we have a complete outage, all of our cameras keep going for slightly over an hour before they'll lose power. We also have a backup power system that should bring it back way before then, so we should never lose those cameras. So that's the kind of things that we can provide to protect our electrical equipment. The other thing we have to protect against is static electricity. And static electricity, we know from our discussion in class, is when we have a built-up voltage in our body that we are dissipating, or from one object and dissipating to something else. And I talked about how you can run around a shag carpet and shock your best friend, your little sister, in my case when I was young, and you sometimes can see and sometimes can hear and usually feel that dissipation of voltage from one thing to another. And there's some things we talked about that we have to help with static electricity. We have grounding straps or bracelets that we can use. We have grounding mats. We have shielding badge. But I said here in our class, the one thing we always do, and now you can guarantee this is going to be a question on the test, the one thing we always do is, number one, we have the thing unplugged from anything electrical. Number two, we touch the power supply because it's the hardiest component in our computer, to ground ourselves to the computer before we reach in and touch any kind of components. Anything inside it, we always touch our power supply first. And we also want to dissipate the power that's in the motherboard by holding down that power supply while it's unplugged for 20 seconds prior to reaching in to make sure we've dissipated the power on any of the capacitors. So what do we do to protect our computers? Unplugged, power supply, 20-second power push before we touch anything inside our computer. And since I started doing that as my rule of thumb, I've had virtually no computer that I know of that has had a problem due to static electricity. I can't say that during my previous years. I mean, before I came here. In order to understand static electricity, I said you need to understand these three numbers, because if you don't understand these numbers, you don't understand why we're dissipating, why we're equalizing our static electricity before we touch things. So these are the three numbers that I said we needed to know. First one was the voltage we need, that before we can even feel that we've dissipated any static electricity, before there's any knowledge that we did at all, we have to have 3,000 volts dissipated. So if you have 2,900 volts dissipate between you and your motherboard, you will not feel it, you will not know, but it still happened. So it has to be 3,000 volts before you can even feel it. If you can hear it, it's been 6,000 volts. If you hear a crack when you touch that thing, that means that 6,000 volts were dissipated when you touched that motherboard, and you probably just heard something. And lastly, if you can see it, if you see that crack, it's 8,000 volts. You dissipated 8,000 volts if you can see that spark of electricity when you touch your little sister. Those are important numbers. Foot stomp, I guarantee those will be on the test. They should be in your notes, and you should commit them to memory. Okay? So that's why we protect against static electricity, and that's why we do those steps every time we go to get inside a computer. This is a picture of a static strap connected right to the metal case on this PC to keep him grounded there. This is a grounding plug that only has a grounding plug right here in the end of it to keep the PC grounded as well. You can get grounding mats. Again, it has to be grounded to an outlet. That's why there's one plug there on this picture of a grounding mat that you can use as well, that you put your stuff on. And then we have anti-static bags that electrical components usually are stored in to keep random static electricity from harming them. The last thing we talked about with electrical interference in particular was EMI, or electromagnetic interference. I talked about how we have projectors that sometimes look really bad, and then all it is that cable is sitting on the power supply to the fluorescent lamp overhead. Because that power supply is causing an electronic field to be, a magnetic field to be produced, and that magnetic field then messes with the signal going through the wire. We can get shielded cables to offer only partial control. The best thing we can do is put them in conduits or make sure they don't run side by side with each other. We did watch the video on this, but there's a video I've got on just showing that you can use an AM radio to detect EMI by just turning it to an off frequency, and you'll hear that get much louder if it's near an electrical component. Okay, I tried to find the video, I took a little break there. So, talking a little bit more about power and power supplies in general, we need to be able to readily identify those things that we've got on our power supply. There's always going to be a label that lists what kind of wattage this power supply has. I also pay attention to the manufacturing date, particularly here at school, because a lot of times we could be using a power supply that's much older than maybe we should. We have vents and some kind of input. This side doesn't show the input of the air, but this is going to be blowing out the back of the BC, and I know that because there's the plug, and ATX power supplies always blow out. But then we have some number of connectors here on the power supply as well. Power supplies come in all different kinds of shapes and sizes, but there are specific ones that go with ATX, and there are specific ones that do not. So when you're looking at power supplies and buying power supplies, you need to make sure you find one that's listed that it goes with an ATX case. They can have multiple numbers of fans, whether they have one 90 millimeter fan, whether they have two 90 millimeter fans, whether they have a single 120 millimeter fan, which is the bigger one here, or whether they have multiple, is in some people's opinion irrelevant. I like a big 120 fan personally, right here, like I've got on these right here. Research has shown that two fans do no better than one fan on a power supply, so you need to watch out for that. If it's costing you more, the big thing is, does it have the ventilation that it needs to pull the air out of the case and blow it out? So in this case, this one's going to be in. It's going to be sucking the air in here and blowing it out the back here, which is going to make it hard for you in this case with this power supply to notice that the fan has gone out, because you can't see it from the back of the case. This is where the back of the case is, right here and right here. It's harder to see than one where you can readily see the fan spinning at the back, and we talked about how that absence of the fan spinning is one of the first indications you can get from a failing power supply. So we've got a number of different power supplies that we can purchase. The big things we need to look at is the wattage and the plugs. Does it have the connectors that we need in order to use it for our computer? Okay. Does it have the minimum wattage, the recommended wattage? What wattage does it have compared to what we compute for our requirements? And does it have all the connector plugs that we need as well for whatever we're going to use this power supply for? I'm going to go to the next one because it's a better picture of some of the connectors. You can get a 20. And I've said you're always going to get a 24 pin or a 20 plus 4 pin connection. What kind of power then goes to our motherboard? Is it a 4? Is it a 4 plus 4? Is it an 8? Depending on what kind of CPU you have, what kind of motherboard you have, those requirements are going to change. And then we've got SATA and what are called Molex connectors, which are all 12 volt. We know that all these connectors are 12 volt other than the motherboard, which is 3.3, and the floppy drive is 5. And these are really interchangeable, and I showed you in class how they make adapters that go from one to the other. So if you've got a ton of SATA connectors and not enough Molex, you can pay 99 cents and get an adapter, or vice versa. You just have to have enough of these total to get done what you want to get done inside your case. Things that we need to know about our power supplies. That we may need to upgrade if we're adding new devices. And new devices can mean new memory, it can mean a better CPU, it can mean a better CPU fan. may mean a better video card, which can drastically change our requirements for power when we put in a new video card. We want to make sure that it has the wattage required to run all of our devices at the same time. During boot up, all those devices are initialized, and maybe during 90% of the time they're not all running, but during boot up, during the post, every single one of those suckers gets power, and if they can't handle starting them all up at the same time, then it may not get found in BIOS. I had the case of a hard drive. I had 3 hard drives in my PC at home. I had not recalculated my wattage for an extended period of time. I had put in a new gamer video card, and one of my hard drives never worked. I sent it back. They sent it back to me and said it's fine. I put in a new power supply, and yeah, they were right. And how stupid did that make me feel? I didn't even look. I actually thought I had an 850 watt power supply. I had a 650 watt power supply inside my PC. I was perfectly positive that it was an 850. It turns out I'd taken my 850 out and given it to one of my kids. So we need to look for those errors when things are working at the same time. We need to not estimate. We need to calculate our wattage required by using either an online calculator or a worksheet that I've given you. Those online calculators are great, and obviously going forward out of this class, you're not going to come back and use my piddly worksheet. You're going to use one of those online calculators to figure out whether your power supply meets the recommended requirements for the system that you're building. So it's really important that we understand how to do that. And I started you out with a calculation sheet where we could go through like a laundry list and say, yes, it's got a motherboard. Yes, it's got a dual core. Yes, it's got a gamer video card. Yes, it's got 4 sticks of RAM. It's got an optical drive. It's got 2 hard drives. It's got no floppy drive, but it's got an expansion card, and it's using 4 USBs, and it's got 2 extra cooling fans. And I do all that math to come out with a calculated number. And that calculated number is what I've just figured out it has to have to run. And I said you can't use that. You have to round that calculator up to the next 50 to get what I would say is our minimum. So if this came out with 295, our minimum is, that isn't 295. 295, our minimum would be 300. And I said I would always add 50 to that to get our recommended. Because if you add a stick of RAM, if you want to do any expansion, I would at least get one that's 50 more than what you come up with as the minimum. And I also said in class that it never hurts you to get a stronger power supply. It runs more efficiently, it doesn't use more power, it actually uses less power. So if you need a 400 and you see that a 650 is only $5 more, get the 650. Because you're going to save power in the long run, and maybe you don't care about it right now because mom and dad pay for the electrical bill, but you might care about it in a few years when you're paying for it yourself. So that gap between what you buy and what you figured out is good. Okay? So we need to be able to do these calculations, and obviously we looked at the online worksheets, and those are great, and those let us really pull down the nitty-gritty of what's in our system to be very precise. And usually those come up with a lower number than this worksheet does. Usually. Except for in the case of a really good gamer video card. My saying 120 on a gamer video card is not going to cover every single gamer video card. I had a gamer video card in my computer that required 2 different PCI power connections in it. That was pulling a lot of wattage. So it wasn't using just 120, I guarantee it. You'll see some video cards that say required minimum 700 watt power supply in your PC because it's saying we are going to suck a lot of power. So you got to have at least that for me to run. So sometimes my worksheet's going to come up less, sometimes it's going to come up more. It's never going to be exactly precise because we're not looking at exactly that make and model like those online worksheets do. Talk about troubleshooting. We need to figure out what things prevent our PC from booting correctly. We talked in Chapter 2 about BIOS codes, those boot codes that listen for that beep. That means that It's probably a memory error. But there are other indications that we talked about in this class. We talked about and pulled power supplies from PCs and tested those power supplies with the power supply connector. We'll be doing that again in Chapter 4. We will be pulling everything out in Chapter 4. We'll be testing the power supply every single time we do it, just so we get good practice at doing that, as well as pulling motherboards, pulling CPUs, pulling memory, pulling everything out, putting it back together. When we go and try to determine what is wrong, one of the terms that we're going to talk about is divide and conquer. We want to divide and conquer. In other words, we want to minimize all the things that could be impacting this PC as we try to troubleshoot it, so we know one thing at a time what has induced the error. Okay? In order to get a PC to boot, we don't need a hard drive, we don't need a CD-ROM, we don't need a floppy drive. We do need memory, we do need a CPU, we do need a motherboard, and we do need a power supply. Those things are required. So one of the things we do in troubleshooting is we learn to start unplugging everything we don't need, seeing if we get BIOS, if we get our post, and then plugging things in one at a time till we figure out what thing caused the problem. When we're talking about power, there's very little we can do other than see the obvious indication that it's not starting, it's overheating, the fan's not turning. Other things that can cause problems with power supply is if my computer runs for 30 minutes and then shuts down, and I open it up and my fan's not turning and I have no other fans, it's very likely that my CPU is overheating and it's turning off the computer until it's cool enough to be turned back on. So we have to start thinking about dividing up the components as much as we can and thinking about them one at a time as we troubleshoot our PC. Okay, so we want to eliminate what's unnecessary and then slowly bring things back in one at a time as we put our PC and try to determine what's wrong with our PC. So things that we can look at specifically for our power supply, we have odors, okay? We have loose cables that we can look for. I said the biggest thing is just the lack of airflow. When you put your hand behind your power or your PC, if there's no airflow coming out of your power supply, something is wrong, because we know that the air flows out of the power supply. I should feel warm air coming out of the back of any PC power supply. It doesn't ever turn off. That's one of the fans in my computer that's always, always, always running. It never, ever, ever stops. So I should always feel airflow out the back of my PC. Okay? We have learned how to test our power supply. Okay? We can open up our computer. We obviously turn it off. We can open up. We can check those connections to the motherboard, to the power supply. Very seldom do those come loose. They have those little snaps that we know about that we have to squeeze in order to get them off. In fact, it's usually hard to get a power supply disconnected that's been plugged in for an extended period of time. That doesn't mean it never happens. And so that's why I would suggest, if you get into troubleshooting or repairing PCs, that $15 troubleshooting part is worth its weight in gold, because if you go up to a PC and it's not starting, the first thing I do is unplug that motherboard plug it into my tester, and before I waste a whole lot of time doing anything else, I ensure that my my power supply is working. Other things which seems obvious to us are not obvious to every user. I've gone to classrooms time and time and time again where my computer won't start, and I go down there and I look, and the surge protector is not on. That red light is not on. They've kicked it, put their foot on it. Some kid's in it on purpose, who knows? But it's off and it won't come on. Or the monitor's not on. The computer's not turning on, and all you do is go and see, hey, there's no green light on your monitor. I think your monitor's gone out. Your PC's working fine. The green lights on your PC are on. There's obviously switches on the back of the computer that can be turned off all the time, and these seem like obvious things, but they're not obvious to everyone. Okay? Is there a UPS involved, and does the UPS work? And is the wall outlet working? And the way to figure that out is I usually go and plug my monitor into the same plug that my PC's plugged into. You know, they go up and down. Same plug almost always works. So if my monitor turns on, then I'm pretty sure my wall outlet's got power. And if it doesn't turn on, then I need to go and call somebody to check the circuit breaker, because it's totally possible, and it's happened. It doesn't happen here like it used to. It used to happen all the time, that whole wings would go out, particularly here in the high school. In the older building, when we had PCs in all the rooms, if everybody was using the PC in room 216, it could trip the power for 216 and thereby affect 215 as well. So sometimes we had circuit breaker issues. We don't have that anymore because we have an old building, but now we got laptops, so there's not a lot of power usage down here. So those are some of the things that we can look at with power supplies. And I do want to point out one thing. Odors are not something to be taken lightly. If you smell something burning, unplug the computer and do not stick your face in it and smell it as strong as you can. Okay? Electrical smoke can be highly toxic, and it's really bad for you. When I was flying aircraft, the first thing you did if you smelled smoke was you do the smoke and fume elimination checklist, which is a boldface item, which is oxygen 100%. You went oxygen 100% before you did anything else, because you could be incapacitated by electrical smoke. And I will carry that one further. When I was a 53 aircraft commander, we were flying across the country at night in the rain in the 53 at moderately low altitude, and my engineer said he smelled something, and he's like, you know what, I think we should set it down. I think I smell smoke. In the helicopter, there are no masks. There is no 100%, and so we set it down in a field, and he climbed. There's an electronic bay that goes basically between the two pilots down. His seat swings out of the way, and we're sitting there, and he climbs, kind of shimmies into this electric bay that's down under the nose of the aircraft, and starts to talk to us, and then all of a sudden his body goes completely limp. And basically he was down there, he's smelling around for an electrical fire, and found it and passed out. And basically the other engineer pulls him out, and he cuts up his chin pretty good, banging it on the bottom of the electrical bay. On his way out, it turns out that they had turned on the windshield wipers, the motor had burned out, and it stayed on and caused a small electrical fire underneath the hood of the helicopter, to put it easiest. So electrical smoke and electrical fire is not something to be taken lightly. The coatings on those wires can be toxic, and especially when I was in a 30-year-old helicopter. It's not like it was to today's standard. So if you smell electrical smoke, unplug it and clear out the area. You don't need to find the smoke to determine if there was a fire. Okay? After the smoke is dissipated, you can open up that PC, and if you see melted wires, there was an electrical fire. Okay? We had something just like that with the sign outside that Mr. Anderson and I fixed this fall. There were some wires that fried and melted good in that thing, and so that's just a caveat that I want to point that out. Okay, so the other thing that can affect us is whether we said that there's a remote wire switch that turns on the power supply, because the motherboard turns on the power supply. The motherboard turns on the power supply. The motherboard turns on the power supply. When you hit that on switch on the back of the power supply, it doesn't turn on diddly squat. It just allows it to be turned on by the motherboard. Okay? So what happens is that there's that P1 plug that we plug into the motherboard. When we push the switch button that this wire goes to a little button down here, when we push that button, it closes the circuit here on this switch that sends electrical impulse through the motherboard to the power supply that says, okay, turn on. And if this switch is undone, there's nothing that's going to turn on the power supply. Now when we plug in our power supply tester, it fakes it. It sends that same signal back to the power supply to tell it to turn on. That's why the power supply does turn on when we plug in our battery tester. So if this is come unplugged, our power supply will not ever turn on. So we need to make sure that the switch, the power supply, is plugged in correctly. So if we've done stuff inside our PC, if we've removed our motherboard, put our motherboard in, put a new motherboard in, and all of a sudden our power supply doesn't work, and my gosh, it worked before, and golly jeepers, I plug it into a power supply tester and it works just fine too, I will suspect this sucker more than anything else that I didn't get it in the right spot. So I need to make sure that I've got it in the right spot, and I've had students swap the reset and the power. They have those two things swapped backwards, and when that happens, when they push the power button, the fan moves for just a second. It goes, Voop. Hey, Mr. Poole, keeps coming on and going off, keeps coming on and going off. It's because when they push the reset button, for that millisecond that they're holding it in, the power supply gets the signal, because it's plugged into the power spot, gets the signal, it starts to start. When they take their finger off, it stops starting, because it just got told not to start. So if you have plugged in your switches, and when you push the reset, it just goes zzz, zzz, zzz. Well, you're not doing anybody favors right there. You've got the two backwards. I don't know if you can see what I just did, but I just locked my screen up and went to Control Alt L, Alt L, Alt L. I don't know what I'm doing. Here we go. Alt L, Control L. There we go. Control L. Okay, so we got to remember to have that switch put in right. Okay, we've talked about this. We don't go and open up power supplies because the big capacitor is inside them. But if we've got a faulty fan, we've got a faulty power supply, can you replace the fan inside a power supply? Yes, but usually it's an indication of something else going wrong as well. And I have done that before and had the power supply work for another year. I've done it before and had the power supply work for another hour, because there was something else. The fan was just a symptom of the failing power supply. So I don't recommend doing that. I recommend getting a whole new power supply if the fan goes out. And you have seen fans that are totally jammed with dirt and dust from being pulled through there. When we did the PCs the other day, you guys had fans that wouldn't turn at all, and that can happen to a power supply. That doesn't mean the power supply is bad. That's what I'm saying. It just means it's not going to get any airflow. So power supplies also kind of go along with form factors and the idea of overheating. Okay, overheating problems can be an indication of the computer just hanging up for a while and doing nothing. New CPUs will slow down and stop for an overheat, and that cools them down, and then they'll come back on and they'll start working again. So a bad power supply or an overheat in general can be one of those indications. We have to check our airflow, check our vents, okay, to make sure what our temperature is. It says CMOS to check the temperature. Really, many BIOSes today will tell us what the temperature of our computer is running. So I can go right in and see what the temperature of the system is. I actually have a scanner that tells me the temperature of every single system in the district. If I was to go to our remote PC in the center of the district on the main network, and I was to remote to that one, I would be able to do a scan with a system that we've got called Newt, and I'll do a quick scan of just a few computers. I'll just do the main set of computers to show you that it can report the temperature to you. And there are programs that you can run in Windows too that will show you the temperature as well. So let me just go ahead and do a scan of, I'm going to do 5, 6. We're going to do servers, and we're going to do those real fast because we'll get through that set of PCs relatively quickly. While that's scanning, we're going to go ahead and come back to that while it's doing the scan. But it's really BIOS, not CMOS, that we use. We can go to the basic input-output system, go into that program by hitting F2 on a Dell, and check out what the temperature is in many of the systems that we've got. If we've got an overheating system, we need to think about replacing the fan inside the case. If you have a power supply that just isn't doing the job as far as cooling, there's nothing wrong with having multiple additional cooling fans inside our system. CPUs that are cooler will make the computer run faster. So the cooler your system is, the more cooling airflow you have through your PC, the faster your PC is going to run and the better it's going to run. So think about putting extra fans. This one, you can see, uses a Molex plug. Some of the cooling fans plug right into your motherboards. Most motherboards have 2 to 3 fan connectors on the motherboard, so they get turned on automatically by the motherboard. And some of them are 4-pin connectors. That means the motherboard not only turns them on, it can control the speed of the fan and turn off the fan. If it's running cool, it just turns it off. So it maintains the fans at what speed it needs to cool it at. So this is an example of good versus bad airflow in a case. In a good case, the air comes in through the front, goes out across the CPU, out through exhaust fans, out through the power supply, and out the back of the computer. If it's coming in and going across and there's very little airflow other than one fan inside a mini power supply, you can have a really hot running case, and that's what the example of this is. And we have some that are designed poorly like that, in my opinion, that don't have adequate cooling on the system. This is just another example of a cooling fan here. This one has a smaller plug that actually plugs into the motherboard as opposed to the other one that was using a Molex. You can see how many vents this power supply has to draw air out of the system. If you've got a power supply that only has a few, or I've seen some that have like that much area to pull air through, nothing down here, then what you really got is a recipe for disaster with cooling in your system like that. Let's see if we've gotten cooling up. We've got some reported back. I can go down here to the, let's see if I can drag this over. There we go. And I can go down here and get the temperature. Let's see if I can find the temperature column in my scan. May have already passed it. I think I did. I don't think it's that far now. Let's see. System temperature, there we go. So let's see. So we got 97 Fahrenheit, 106 Fahrenheit, 108 Fahrenheit. They're all pretty good right now. We know that the high end where electrical components fail is 185 degrees. 185 degrees is the temperature which electrical components fail, right? We should know that off the top of our head. I did this scan range small on purpose so that I get it done faster. So you can see none of ours are excruciatingly overheating. That's great. And this says it's using the CPU temperature. So that's the hottest part of that PC probably, and it's running 108 degrees. If I wanted to do more, I could go do 1 through 4. I could start this over again. We'll see what the staff PCs are running like in the high school while we go on. We'll let that get started there. Okay, so good cooling is important. That's it really for Chapter 3. We talked about electrical power, AC, DC, understanding what wall current is, what the DC current is, what the power supply does as far as rectifying and transforming our power, what our voltages are that come out the back of our power supply, and then being able to figure out the total power that's required of the power supply and making sure we've got a power supply that's sufficient wattage. We talked about the different kind of power failures or problems that we can have, being spikes, brownouts, and blackouts, and the things that we've got to protect against those being surge protectors, power conditioners, and uninterruptible power supplies, or UPSs, that we've got throughout the school, the different kinds of ways that we can protect ourselves against power problems. We have taken apart PCs, removed power supplies, tested power supplies, and we talked extensively about some of the things that can happen because of bad power, and how we can detect and eventually possibly purchase and replace power supply. As well as last class, I did the presentation on the power supply as a demonstration of what the projects are going to look like going forward in the class and what kind of things we're going to be doing. If you have questions after today, since the test is not today, the test is next class, you need to do two things. You need to, number one, make sure your notes are current. And the notes include not only the things that we've talked about in class, but also those things that were in our course reading that you were assigned, because all those things are things that could be on or will be on your test. So when you're looking at your notes the remainder of the class period today, I want you to make sure that you go through these readings and that you've got notes from those things on the test, because of course they'll be hidden during the tests themselves. If two of these were assigned and some of you guys didn't get them done, make sure you do those blended activities that were assigned in class. All 5 of them were not assigned in class, so make sure you get the first 2 done. Make sure you understand how to do the power supply calculations. If you want to print out the wattage worksheet and take a look at a couple different PCs online, maybe pick one out with your table partner there and say, hey, let's both do this and see if we come up with the same number. That's an excellent use of your time during the remainder of the class. And then obviously, like I said, make sure these things are in your notes and you feel like you're prepared for the class, for the test. So the test will be next class after this review. You have time the remainder of this class and obviously up until then to make sure you go through your notes, make sure you reread the reading, and that you're ready for the test come next class. I will tell you that historically, I have a wide spread of grades on this test. In many of the tests, everybody in the class does about the same. This one in particular, I tend to have A's and D's and not have B's and C's, because people either understand and can do the calculations, understand what we've talked about in class, or they have not. And if you don't, then you need to email me. Realize that if you email me a question, very likely I'm going to email you back a video. I'm going to talk just like this through the problem, through the question that you had, and send it out to everyone, or possibly just to yourself and post it on our Moodle calendar so that people can see that as well. If you missed a class during this chapter and you haven't watched the chapter or that class, you need to make sure you go back and watch that class as well. That's all I've got for you guys today. Good luck on your test next class.